Hi, I'm Jenna Tran, and this is my Physics 2211 Lab 02 video on projectile motion. In this lab, I analyzed real projectile motion using tracker video analysis, developed two computational models, one with gravity only and one including air resistance, and compared the predictions of those models to experimental data. The fundamental physics principles used in this lab are Newton's second law, also called the momentum principle, which is F net equals ma. This tells us that the net force acting on an object determines how velocity changes. For projectile motion, gravity provides a constant downward force, as shown in the second equation. And in the gravity-only model, this is the only force acting on the object. In the drag model, we add air resistance, which gives the force of drag equal to negative b velocity squared times velocity hat. This force depends on the speed of the object and acts opposite in the direction of motion. The system in this experiment is the projectile. The surroundings include Earth, which provides gravity, and the air, which provides drag. To collect experimental data, I filmed a projectile in motion and analyzed the video using Tracker. The video was filmed inverted, so the coordinate axes were flipped during analysis. Tracker allowed me to extract position data over time in both the x and y directions. From this, I observed that horizontal motion appears nearly constant, vertical motion accelerates downward due to gravity, and the trajectory forms a curved path. These observations guided the construction of my physics models. From the tracker data, I plotted x versus time and y versus time. The x position increased nearly linearly, indicating approximately constant horizontal velocity. The y position decreased with increasing downward curvature, consistent with constant downward acceleration due to gravity. However, the horizontal velocity was not perfectly constant. This suggests the air resistance may be present. This motivated testing both a gravity-only model and a gravity plus drag model. For the gravity-only model, F net equals F grav. This predicts constant velocity x, linearly changing velocity y, and a perfect parabolic trajectory. For the drag model, F net equals F grav plus F drag. Since drag depends on velocity squared, it reduces both horizontal and vertical speed over time. This predicts decreasing velocity x, a reduced range, and a trajectory that deviates slightly from a perfect parabola. The drag coefficient that best matched the data was b equals 0.45. And I implemented both models using numerical integration in VPython. At each time step, I calculated net force, updated velocity using Newton's second law, and updated position. For the gravity-only model, F net equals F grav. For the drag model, F net equals F drag minus b velocity squared velocity hat. The only difference between the two codes is that the addition of the drag force. Initial conditions used in both models were all the same, so same initial position, same initial velocity, same mass, same time step, etc. This ensures a fair comparison between models. Here I compare the tracker experimental data, the gravity-only model, and the drag model. The gravity-only model predicts a longer range than observed. The drag model with b equals 0.45 matches the experimental trajectory much more closely. This suggests that air resistance plays a measurable role in the motion. Terminal velocity occurs when the net force becomes zero. F grav plus F drag equals zero. This means acceleration becomes zero and velocity becomes constant. The gravity-only model does not predict terminal velocity because no drag is present. The drag model does predict terminal velocity during vertical motion if the object falls long enough. To experimentally measure terminal velocity, I could drop the object straight downward from a large height and track its speed as it approaches a constant value. Comparing the two models, the no drag has constant horizontal velocity, parabolic trajectory, and it overestimates the range. With drag, it decreases horizontal velocity, slightly reduces height and range, and matches the experiment more closely. This shows that including realistic forces improves predictive accuracy. Also, conceptually speaking, if the object were thrown straight upward with the same initial speed, without drag, the time to return to the ground would be symmetric and determined only by gravity. With drag, the object would take longer to reach the ground. This is because drag slows the object more during ascent than descent, breaking symmetry. Thus, air resistance increases total flight time in vertical motion. In conclusion, some sources of error include video resolution and tracking uncertainty, axis calibration inaccuracies, frame rate limitations, the issue of assuming constant drag coefficients, and neglecting spin effects. Some improvements would be to use higher frame rate video, use better lighting for tracking, measure mass and cross-sectional area more precisely, and drop the object from a greater height to better observe drag effects. The final takeaway is that projectile motion is governed by Newton's second law. A gravity-only model predicts ideal parabolic motion. However, real-world data uses small deviations due to air resistance. Including a quadratic drag force significantly improves agreement between model and experiment. This ultimately demonstrates how refining a physical model by including additional forces leads to more accurate positions.